Now we have something called a mole ratio. And a mole ratio, just like our other quantities from this chapter, we have a checklist or keywords that we're looking for to tell us when to use it. And for a mole ratio, we're going to use that when you see yourself going from one thing to another thing. Okay, and we're going to get that mole ratio from either a balanced equation, usually, or we can also get it from a formula. But they both mean the same thing. And let me show you what I mean here. Let's start with formulas. How about, let's say we have aluminum oxide. Well, what this means is that for every 1 mole aluminum oxide, you have 2 mole aluminum. You have 3 mole oxygen atom. And this should make sense. If you have one of the parent molecule, then whatever the subscripts they mean, well, that's how many moles you have. And so we can say something like this over here. We could say, let's say we had CF4, carbon tetrafluoride. Well, that means for every 1 mole of carbon tetrafluoride, it means you have 1 mole of carbon and 4 mole of fluorine, and so forth. And this is very handy. Now remember what a mole is. Mole is 6.02 times 10 to the 23rd of anything per mole. And so that's actually a counted quantity. And what this does is it helps you count what do you have. Because moles are much easier to deal with than trying to count out individual atoms and molecules. Okay. And so we can write these relationships as conversion factors. We can say for every 2 mole aluminum, you have 1 mole aluminum oxide. And we can write it both ways. Remember, we can flip over any conversion factor and get the other one. And why would we do that? Because we're going to be canceling units, the units in this case being the moles. And down here with the carbon tetrafluoride, we can say for every 1 mole carbon tetrafluoride, you have 4 mole of fluorine atoms, and so forth. And we can write these down as conversion factors. So what if we were asked, well, how many mole aluminum in, let's say, 8.0 mole aluminum oxide? And we would see, now remember, what's our keyword for using our mole ratio? We have to be going from one thing to another thing. And so where are we going from one thing to another thing? Well, we're going between the aluminum and the aluminum oxide. So we are going from one thing to another thing. And so I know I'm going to need the mole ratio between them. Keeping in mind, what does it mean when we say moles aluminum oxide, moles aluminum? It's the ratio between the two. So how many do I have here? Well, I have 2 aluminums for every 1. 2 aluminums for every 1 aluminum oxide. Okay, and so we would actually write that out. We would say 1 mole aluminum oxide for every 2 mole aluminum. And it's not important which one we put on top or which one we put on bottom, because we're going to fix that when we set up our setup. And of course, we always do our setups. How do we do our setups? We draw a line, we draw another line, and then we start with our measured number. What's our measured number? Here's our measured number right there. And it's not just 8, and it's not just 8.0 mole, it's 8.0 mole aluminum oxide. You have to make sure that you're always labeling what you have. We'll extend this line out just a little bit. And so 8.0 mole aluminum oxide, and then we use our mole ratio as a conversion factor. And so what do I have to have down here? Well, I have to have on the bottom, to get the units to cancel, it has to be the moles aluminum oxide down on the bottom, and there's 1. And of course, what does that mean? It means we're flipping the mole ratio, And so 2 mole aluminum, and we're done. And so we put this in our calculator, and I don't think I need a calculator for this, and 2 times 8.0 gives me 16.0 mole aluminum. And I know I'm set up right because moles aluminum cancels, and it leaves you with moles aluminum oxide cancels, pardon me, and that leaves you with moles aluminum. So we have set this up so that the moles aluminum oxide cancels. And how do we know we needed that mole ratio? Because we were going between 2 different things, aluminum and aluminum oxide. Aluminum is not aluminum oxide, and aluminum oxide is not aluminum. And so we can do something very similar. We'll try another one. How about, let's take that carbon tetrafluoride. How many mole fluorine in 1.81 mole carbon tetrafluoride? And since we're going in between 2 different things, we have moles fluorine, moles carbon tetrafluoride. Well, then I need the mole ratio between the 2. What's the ratio? Well, it would be for every 1 mole CF4, carbon tetrafluoride, we have 4 mole fluorine. Where does that 4 come from? It comes from the formula. What does the formula mean? That's what a mole of carbon tetrafluoride looks like. And so now we're going to go ahead and draw a line and draw another line. Once again, starting with our measured number. What's our measured number? It's right up here. It's the 1.81 mole CF4. And so we start with our measured number, 81 mole carbon tetrafluoride. And I'm going to have to get the carbon tetrafluoride in my conversion on the bottom so that units cancel. As you know, we want them diagonal from each other, and we always are looking at units, and we're always making sure that units cancels. So we're going to have to flip this over, the mole ratio over, and put the 4 mole fluorine on the top and the 1 mole CF4 on the bottom, and we're done. And so we put this in our calculator, and we go 1.81 times 4, and that gives me 7.24 mole fluorine. Okay, now it's very important that we have everything labeled, and here's the reason why. If you look, there's 2 different kinds of moles up there, and if you don't have it labeled with moles fluorine or mole CF4, if you just have 4 mole or 1 mole, well, you got a 50-50 chance of putting it down right, and that's not good odds. So make sure that everything matches, and by what I mean by that is that units cancel. Okay, so that's how you do mole ratio with a molecule or something like that. Now, the more common way that we're going to be using a mole ratio is within a formula, because we're fixing to do some calculations using mass quantities. So let's say we have this balanced equation here. Okay, this equation is balanced, and it's the reaction aluminum with oxygen gas to make aluminum oxide. Now, what this really means when we have a formula, and this is the key, this is where you really need to understand, this actually means 4 mole to every 3 mole gets you 2 mole. When we have a balanced equation, really what we're saying is that this is the recipe to put together aluminum oxide from aluminum and oxygen gas, is that you take 4 parts, 4 moles aluminum for every 3 moles oxygen will give you 2 moles aluminum oxide. This is sort of like putting together a bicycle. It's one of the examples that are given. Well, for every bicycle, you need 2 wheels and a frame. And so that's your recipe. And so you can make as many bikes as you want. You just need to make sure you have enough wheels and enough frames to go with them. Okay, so we can actually write out mole ratios from this depending on which pair we're going together. So what we can do is say, well, what if I was going between aluminum and oxygen? Well, then the mole ratio between them would be 4 mole aluminum for every 3 mole oxygen. And what if we were going in between, say, the aluminum and the aluminum oxide product? Well, we would say for every 4 mole aluminum, we get 2 mole aluminum oxide. And finally, we have another combination that we go in between. How about between the oxygen and the aluminum oxide? And these are all our pairs that we could possibly have. And so that would be what? 3 mole oxygen for every 2 mole aluminum oxide. And of course, we can take any of these and we can flip them over. Why would we want to flip them over? Because we're going to be using this as a conversion, just like we just did above. We're going to be using our mole ratio to go from one set of moles to another set of moles. And so if we look at this reaction up here, we have these 3 mole ratios and 6 if you flip them. And how about if we had a problem that looked like this? How many mole oxygen to react with, let's say, 8 mole, 8.0 mole aluminum? Okay. And we look at this, and what's our rules? We're looking for keywords. We're always looking for keywords. Now, right now, we only have one set of keywords that we're worried about, and that would be that we're going from one thing, oxygen, between another thing, aluminum, which means the mole ratio that comes off of that balanced equation would be 4 mole aluminum for every 3 mole oxygen. And ignore everything else. This is important because I'll get the question, well, I see the aluminum and the oxygen, but what about that aluminum oxide on the right-hand side? Well, it's not part of the problem. When we do these problems, we do it between pairs. So your equation could have 3 things in it, could have 4 things in it, could have 5 things in it. All we're interested in is what are you going in between? So we'll ignore the aluminum oxide because it doesn't appear in the problem. Okay, so now we are ready. I don't see anything else over here that I need. We're ready to use our mole ratio as a conversion, and let's go ahead and do that. So why don't we go ahead and draw a line, and we'll draw another line, and we'll start with our 8.0 mole aluminum. And now I need moles aluminum on the bottom, so I'm going to have to take that mole ratio that we just pulled down off the balanced equation, and we're going to flip it, and so that becomes 3 mole O2 for every 4 mole aluminum, and that should be it. And so we make sure that our units cancel, and sure enough, moles aluminum cancels with moles aluminum, and that leaves us with moles oxygen. So this just gives us something I can put into my calculator, and that would be 3 times 8 is 24 divided by 4 would be 6. Let me change colors here. Would be 6.0 mole of oxygen. Now, as far as sig figs go, your measured number in this case is 2 sig figs. This is exact or counted, are these mole ratios, because it tells you for every 3, count them out. I need 4, count them out. And so, but our answer here should be 2 sig figs, and it is. Okay, so let's do one more of these using our balanced equation, and then we're going to pull everything together. And let's say we had this combustion reaction balanced. And I want to know how many mole CO2 from, let's say, 6.0 mole O2. Now, it doesn't matter whether we have them both on the same side, or if one's in the product or one's in the reactant, or they're both in products. It doesn't matter. All we're caring about is the pair. So where's the pair? Here's the pair right there. It's between CO2 and O2, and we're ignoring everything else that's in the problem. And so I look and I see a 2, and there's an implied 1 there. So I say 2 mole O2 for every 1 mole CO2. And we don't worry about which one's on top, which one's on the bottom. We're going to fix that with our setup. And so now, since the only thing that's going on up here, we've got to always ask ourselves what's going on, is we're going from one thing to another thing. We're going from oxygen to CO2. So we're going to draw a line. We're going to draw another line, and we're going to start with our measured number, 6.0 mole O2. And it looks like the way I wrote down the mole ratio, we're going to have to flip that to get moles O2 on the bottom. Never be afraid to flip things, and so that becomes 1 mole CO2 for every 2 mole oxygen gas, and we're done. All we got to do now is just put this in our calculator, follow our rules for significant figures, and this is 3.0 mole CO2. Okay, so we have our mole ratio, which we can get off the balanced equation. And so a mole ratio, usually we say moles of B, wherever we're going, over moles of A, although it doesn't matter which one you put on top. And so we say, we'll use when we see one thing, A, going to another thing. And we'll just kind of highlight that's a B. A to B or B to A, it doesn't matter. Okay, so this is our keyword for that. Now recall, we also had something called the molar mass, and that's grams per mole. And the grams came from the periodic table. We added them up, and it's grams per mole. And anytime we see grams, because what do you see in the molar mass? You see grams per mole. But anytime you see grams in a problem, then that is going to be when you're going to use your molar mass. All right, and you get that from the periodic table. And then we had Avogadro's number, which we won't use too much of, but that's 6.02 times 10 to the 23rd of anything per mole. And usually that's when we see number of, or how many, atoms or molecules. So the procedure is we're going to go through every problem, and we're going to look and see, what do we have in the problem? Do I see myself going from one thing to another thing? And we would say, either you do or you don't, in which case you would use your mole ratio if you do. And you look in the problem and you see, where do I see grams? And you can have more than one place that has grams. And if you do, then you need the molar mass. You go to your periodic table and you find what it is that you need from the periodic table, the masses, to get your molar mass. And then finally, if you're asked, how many or the number of atoms or molecules, then you need Avogadro's number, 6.02 times 10 to the 23rd per mole. Okay, and then once you pull those down out of the problem, then you ignore the rest of the problem. You just ignore the problem. A lot of times it's the words that get in the way. So if we're just looking for grams and we do the molar masses and we're looking for the mole ratio between the two, then we can pull those down, draw ourselves a line, and be sure that units cancel, and we will get the right answer, because really that's the goal. So let's try a problem like that. Let's go back to my favorite balanced equation, which is the oxidation of aluminum. And we go 4 aluminums plus 3 oxygens gives me 2 aluminum oxides. Okay? And I want to know how many grams aluminum oxide from, let's say, 16.2 grams aluminum. All right, so we're going to run down our list. We look at the problem and we look at our balanced equation, and we're going to run down our list of keywords and key phrases that we're looking for. And so what do we see here? I see, if I'm going from one thing to another, if I see anywhere I see grams or how many atoms, these are the things that we're going to use. And so we go back here, and the first thing I see is that we are going from one thing to another thing. We are going from between grams aluminum to grams aluminum oxide. So we are going between two things. And if we're going through two things, then that means we need what? We need the mole ratio, and that comes directly off the balanced equation. So we're going to say 4 mole aluminum for every 2 mole aluminum oxide. And by the way, these numbers here go nowhere else but into the mole ratio. This is the sole purpose of the balanced equation, is to get you the mole ratio. Okay, so we definitely are going between two things. Now, how about, do I see grams anywhere? And the answer is yes, and I see it in two different places. I see grams aluminum oxide there, and I see grams aluminum over here. So I'm going to need the molar mass of both of these in moles per gram. So let's do the grams aluminum, and I look on the periodic table, and I see that if I round to one decimal place, it's 27.0 grams aluminum for every mole aluminum. And I caution you, do not put that 4. This happens all the time. Do not go 4 times because you see the 4 in front of the aluminum. Don't do that. People do that all the time. You're just using the balanced equation is just for the mole ratio, and here you're using your periodic table to get your molar masses. So what do we have here for aluminum oxide? Well, aluminum oxide would be what? It would be 2 times 27.0 plus 3 times 16.0, and I got those 3 and the 2 off the equation, and I got the 27.0 and the 16.0 I got off the periodic table, and that gives me 102.0 grams aluminum oxide. Always label these things for every mole aluminum oxide. And so I've gone through and I have found all of the molar masses. There's 2 of them. Now, last thing we ask ourselves, do we see, are we going to atoms or molecules? And the answer is no. So we don't need anything else. And so now we are done with the problem itself, the words. We're done with the equation. Now all we got to do is really just set things up so they cancel. And so we're going to draw a line, a lot longer line. There we go. And we'll draw another line. And what are we going to start with? We always start with our measured number. Where's our measured number? Well, it's the 16.2 grams aluminum that you're starting out with. That's what you measured. You're looking for the grams aluminum oxide. So we start out with our aluminum, and we say 16.2 grams aluminum. And now it's a question of matching, just like we've done on earlier problems where we combined more than one conversion factor. At this point, it's matching. What do we need to match up? Well, we start with grams aluminum. That's what I need to match up. Remember, it's got to go down on the bottom for our next conversion factor. And so where do we see grams aluminum? Well, I see grams aluminum right there, which means that is what goes next. And I'm going to have to flip this over to get grams aluminum on the bottom, but that's okay. And so we say a mole aluminum, we're going to flip this over, is 27.0 grams aluminum. And just like we've done on previous conversion problems, which is what this is, we use a check mark so that we don't accidentally reuse our grams aluminum again. Okay? And I know that's set up right because grams aluminum canceled. And if we stopped here, we'd have the moles aluminum, but that's not what we're after. We're after the grams aluminum. So what would come up next? Well, what comes up next is whatever has moles aluminum in it. Now, the molar mass of aluminum over on the right-hand side's got a check mark, so we wouldn't want to reuse that. That would just send us back where we started from. So we look and we look and look, and I see moles aluminum right here. And so that's what goes next. And just like on the previous conversion, we're going to have to flip it to get it to where moles aluminum are on the bottom. And so we say 2 mole aluminum oxide for every 4 mole aluminum, and we put a check mark through it so we don't reuse our conversion factor. And then finally, seeing that moles aluminum cancels moles aluminum, finally we have the only one left up there is the molar mass of aluminum oxide. And it's going to, and I know it's right because look, it's going to match up with the moles aluminum oxide. And so we go ahead and looks like we can leave it like it is this time. And so we say 102.0 grams aluminum oxide for every mole aluminum oxide. And we're done. All right. And so whatever you do with these conversion factors, don't mix them. If you notice, and I'm going to emphasize this again, that 4 on the 4 moles aluminum and the 2 moles aluminum oxide, these guys, those came from the balanced equation. Sometimes people want to say they want to put a 2 here because they say, well, there's 2 moles. Well, no. The 2 of the 2 moles is handled by the mole ratio, okay? Or don't put, sometimes people want to put the 4, they want to put a 4 times over here because they see a 4 in front of the aluminum with the balanced equation. Don't do that. You're mixing things when you do that. Okay, so when you do your mole ratio, it's just the numbers off the balanced equation. And if you do your molar masses, it's just the numbers off of the periodic table. Now we can go ahead and put this in our calculator. And we go 16.2. We multiply everything on the top times 2. And then we divide by everything on the bottom in parentheses. So we go divide 16.2 times 2 times 102 divided by parentheses 27 times 4 close parentheses, and I get 30.6 grams. 30, let me change colors here. 30.6 grams aluminum oxide. So that's not what you'd get from that quantity of aluminum. You would predict that you would get 30.6 grams. And I made sure to do sig figs, so they got 3 here, 3 there. This is counted or exact. Mole ratios are always counted. And there's 4 there, so our answer should be 3 sig figs, all the way down to the bottom. Okay, so let's do another one. We'll do one more, show you how to do this. And so how about, let's see, let's take this balanced equation. Let's do our combustion reaction again. There we go. And this time I want to know, well, how many grams of water from, and let's just go for moles. Let's say from 0.500 mole CH4. Okay. And this is just to show you how, as long as you're following the checklist, that you can't help but get it right. And so how are we going to do this? What we're going to do is we're going to go through, are we going from one thing to another thing? And the answer is, well, yes, we are. We're going between methane, CH4, and water. So I need the mole ratio between those two. And what do we have here? I have a 1 there, and I have the 2 in front of my water. And those are the 2 things that I'm going in between. So I'm going to use these as my mole ratio. So I say 1 mole CH4, methane, for every 2 mole H2O. So I've answered the first question, which is, am I going between 2 things? And I am. So I need the mole ratio between the 2. The second question I'm going to ask myself is, where do I, and you don't necessarily see grams, but I do. I see grams of water. And I do not see grams of methane over here. So you only need whatever has the grams. And if you add up the molar masses for water, water is 18.0 grams H2O for every mole H2O. 16 for the oxygens, and you have two hydrogens makes 18. And so I pulled down everything that's something to something. That's the moles CH4 to the moles H2O. And I pulled down the molar mass for water because it is the only one up there that has grams attached to it. Nothing else has grams attached to it. If it doesn't have grams, you don't use the molar mass. If you're not going from one thing to another, you don't use the mole ratio. But we are, and we do have grams water. So now we have everything we need. You see, you don't have to really memorize setups and such. You just have to be able to look through the problem and find what it is that you need. And so once again, we're going to start with our measured number, and that's 0.500 mole CH4, otherwise known as methane. And now I'm looking for mole CH4. Where do I see it? Right here. And so I'm going to have to flip this over because I don't see mole CH4 anywhere else. And so we say 2 mole H2O for every 1 mole CH4. And we put a check mark through it so we don't reuse it. And the only thing we have left is also the only thing that has moles H2O. If you have more left over than you need, then you did something. You did something not quite right. And so we're going to leave that molar mass of water like it is because we have moles H2O on the bottom. And we're done. We can go ahead and make sure that moles CH4 cancels, moles H2O cancels, and we're left with grams water, which is the very thing that we are looking for. And so we go 0.5 times 2 times 18. Everything else is a 1 on the bottom, so we don't bother with that. And it is 18 grams. How about that? It's a coincidence, but that's what it is. 2 times 5 is 1, and 1 times 18 is still 18. So you get 18.0 grams of water as your product. 18.0 grams of water. Okay. And so the bottom line is that you're going to be pulling down whatever it is that you need to be able to do the problem. How about let's go grams to moles. How about if we have this reaction right here? Let me change colors. How about we have the reaction of hydrogen gas with oxygen make water, and that would be 2 H2s plus an oxygen gives me 2 water molecules. And so I would say, well, how many grams of oxygen gas to get 0.250 mole H2O? Okay. And so it's similar to the other problem in that we're going from something to something, but we still have to decide, what is it that we actually need? And so it looks like I'm going between O2 and H2O. So I need the mole ratio between the two. So that's 1 mole O2 for every 2 mole H2O. And I'm pulling it off the balanced equation. And the only place where I see grams is O2. And that's 2 oxygens at 16.0 apiece gives me 32.0 grams O2 for every mole O2. And I have everything I need. So I can sit down here and draw myself a line and draw another line and start with my measured number, 0.250 mole H2O. And I want to use my mole ratio, which is already set up, so I don't have to flip it over. And I know I'm going to put a check mark through there, and we'll make sure that we are canceling, and we are. And then finally, I have my molar mass. And we're done. Do you see how easy that is? So the big step, this answers the question. How do I determine what I need from the problem? And where do I begin? How do I need to determine what's in the problem? You look, see if you're going from one thing to another thing. You look and see if you have anything that has grams, and you don't always have grams. If you're just going from moles to moles, then you wouldn't need anything other than mole ratio. So say 0.250, and that would be times 32 divided by 2, and we get 4.0 grams. And we're going to go sig figs, we better go out 3, and that's grams O2. And that is how many grams of oxygen you would need to make 0.25 mole of water. You would need it right on the nose, 4.00. And of course, this is trailing zeros are significant if you have a decimal. So that's 3 and 3. And so our answer should have 3 sig figs. So that's how you use all the pieces to solve these problems.